and this fight chair. My name is He Siming from Concordia Media School. Professor.
I'm Wang Xunming from National Aviation University.
My name is from National United University.
So my name is Deng Yingchen from the National Taiwan Ocean University.
My name is Junyan Lin from Suzhou University.
And three teams can introduce your members. Reporter.
From Team Maxwell and Wang Yanjun,
And opponent.
My name is Martin from the Niners. This is Ethan, Myron, Wuju, and Andrew.
Reviewer.
这个 reviewer 他的投影，这边出来吗？这边他的投影出不来。出不来，那边
没关系，你可以用。我看那个。
这是李轩明，这是快李一鸣。
Okay. We want we recommend.
你有没有切分享过？对。现在问题他没刷到，那边一台电脑看看。因为我现在bypass过，没有进去。那电脑
如果开暗的话，你要翻译成。
因为那电脑它输出信号太慢。
那个是电脑的问题。我觉得你申请他们那个组内换电脑，应该就可以解决。
But maybe connect is not good. Okay. We want to start with this profile. Opponent, please choose one problem to challenge. Okay. 1 minute.
We would like to challenge Lotto.
Number. Number.
Number 3.
Number 3. Reporter, you have 1 minute to consider.
Reject.
Reject. Change another.
So we would like to challenge number 2, Chairman.
Number 2. Accept. You have 5 minutes to prepare your report. Okay, please. Okay, please read write the reporter name.
就是把人家对的那个，如果你看得到的话，你可以，可能都有手势嘛，
I'm Wen Kai-Tai, a reporter from Team Maxwell. And today, I'm going to be reporting problem number 2, air muscle. So this is the problem statement. We have to place a balloon inside of a cylindrical net that we may sometimes use to wrap garlic and inflate the balloon. The net will expand and shorten. We have to investigate the properties of such a muscle. So, yes, as you can see in the video, the muscle will pull on something we tie it to. So, I think that the keywords for this problem statement are going to be that the net will expand and shorten. And I think the main focus of this problem is going to be the force exerted by the muscle, and some measurements of the muscle, such as the length of the muscle, the width of the muscle, the volume of the muscle, and the pressure inside of the muscle or inside of the balloon. Okay, so first, let's talk about my experimental setup. So I connected the muscle on one side to a force meter to measure how much force it can exert. On the other side, there was a T-shaped tube that was connected on one side to the balloon, and on the other side to a pressure sensor and the pressurized air input. So first is my preliminary observation. So as you can see, when we inflate a balloon without any constraints, except for the net, the muscle will contract and its length will shorten as it is being inflated. Second, we measured the pressure using our pressure sensor. As you can see, the pressure remains actually quite constant throughout the entire process. So next, let's talk about the force that the muscle will be able to exert. So we can divide it into 3 stages. For the first stage, we observe some quite a linear growth in terms of the force the muscle is able to exert. So you can see in the video. In the second stage, the muscle reaches approximately its maximum size, and the growth of the force that it can exert slows down, and we can even see a slight decrease. So I think that's because the net is constricting the balloon such that the balloon can no longer grow. And so the muscle cannot contract even further, and so the force exerted by the muscle does not increase any further. And in terms of why there is a slight decrease that can be observed in the latter parts of the plateau range, when the balloon is inflated to such a size that it almost reaches the volume of the net itself, the length of the entire muscle is not shortened anymore. Instead, it might even begin to lengthen again. So that's why the force we measured actually decreased a bit. And in the final stage, when the balloon and the net reach their critical value and the force from the air pressure exceeds the maximum force that can withhold, the balloon bursts, along with the net as well. Next, let's talk about my theoretical attempt. So when we pump air into a balloon, the air pressure inside of the balloon will push out, causing the balloon to expand. And what is the effect of the net? So when the balloon expands, since the net is of a constant length, and the balloon's width will grow. So since the net is of a constant length and the length is much greater than the width of the net is expanded, and so the length of the net is shortened, and that's what we observed as the contraction of the muscle itself. Next, let's talk about a theoretical attempt. First, as the muscle itself, I believe it's actually quite similar to a spring model, as it lengthens when you pull on it, and also contracts when we pump air into it. It is also supported by relevant literature, the validity of this method. So we will use Huxley to kind of model the muscle, and since, as we mentioned before, in the preliminary observation, the growth is actually quite nonlinear. So we added some terms related to the length of the muscle and the pressure of the inside the balloon to account for this nonlinearity. Next, we will introduce a simple geometric approximation for the balloon. So we'll consider half of the balloon to be a cone and the other half to be a half sphere. We assumed a constant rate of change of the volume, And so we derived it, and we arrived at these two equations that tell us about the radius and the height of the cone, which we can use to derive the width of the balloon and the length of the balloon, which will help us in calculating the entire length of the muscle. So the C will be determined experimentally. So in order to determine C, we pumped air into a measuring cylinder submerged in water. After pumping air into the measuring cylinder for a known amount of time, we measured the volume, and so this is how we determine C. And next, since there is only one Finney constant in our equation, we fitted it to our experimental results. And we can see that it actually matches to our theory incredibly well. And since as we mentioned, there is only one Finney constant in the form of K, I think that this method is rather valid. And also, the K will be related to the muscle and the net and some inherent properties exhibited by them, which we can fit with experimental data to more quantitatively compare different nets and balloons. Next is the changing length. So as you can see, the changing length actually has two main stages, quite similar to what we observed with the volume of the force exerted by the muscle. So in the first stage, there is a linear stage where the length decreases linearly, and in the second stage, the length decreases slowly, as we also saw with the force, and we fitted our theory to this and found a pretty close match. Next, we're going to talk about the force exerted by the muscle. So we will only consider the pressure acting in the direction, in the direction of the force that is being exerted. And so we'll consider the cross-section area of the balloon to be where the pressure is exerting the force. And so we'll assume the widest part of the balloon to be that cross-section area. And we can use this simple equation to arrive at this equation. So after we calculated this, we actually found results that were similar to measurements, experimental measurements. Next, I tried different parameters and did some different experiments. First, I changed the length of the net. So as you can see, as we decrease the length of the net, the force exerted by the muscle actually decreases. However, after, for example, the 25 centimeters mark, the force decrease is significantly less, or the force stops decreasing at all. Also, the red line symbolizes when the balloon bursts. They also have quite different growth patterns, as you can see here. So we plotted the different lengths of the net and the mass force that they were able to exert. And for our theory is that the net will constrict the growth of the balloon, so we assumed that the shorter the length of the net, the less force the balloon will be able to, the muscle will be able to exert. However, we can see in the 15 to 25 centimeters range that the force we actually measured were of a similar value. So we recorded the balloon's growth to find out why. So I think that when the length of the net is below a critical value, the max force that can be exerted by the balloon actually stops changing that much. Yes, and as we mentioned, we recorded the balloon's growth with videos, and we can see that below this critical value, the balloon is able to fill the net completely. And so the growth of the muscle is dictated by the growth of the balloon, which still continues to grow in length, which causes the maximum force that can be measured to decrease. However, above this critical value, the balloon does not fill the net, no matter how much we inflate the balloon before it bursts. So we can conclude that changing the balloon filling the net will significantly decrease the force we can measure. Next, we change the size of the balloon, so the parameters we used were 5-inch, 8-inch, and 10-inch balloons, and all of them were round balloons. So we can see a similar experimental results here. So there is a cluster of similar valued force that we were able to measure here. I think that we also recorded the growth of the balloon. We can see that after this range, the balloon also does fill the net completely. And in this part, before the balloon grows to the size of the balloon becomes too large, the balloon does not fill the net no matter how we inflate it, which confirms our hypothesis earlier. Next, we changed the mesh size of the net, and so we were able to see that changing the mesh size does not significantly, say, decrease the max force that we were or change the max force that we were able to measure. And so, for our conclusion, for our observations, we found that the pressure remains almost constant in the entire inflation process, even until the balloon bursts. For our theory, we derived some theory for the width and the length of the muscle, and we fitted them to our experimental pixels and found a rather close match. Also, we can use the fitting constant to determine some properties inherent of the balloon and the net. And finally, for our experiment, we characterized the different growth stages of the balloon and reserved some parameters, including the length of the net and the size of the balloon. And we also concluded that the balloon filling the net decreases the maximum force reading of the muscle. And that's all my report. Thank you.
Okay. Show question.
Can I see your page 41?
41?
Yes. I have a question regarding your parameters. Did you measure the mass of the mass acting on the balloon?
What do you mean the mass acting on the balloon?
So any mass that was added to the system, or like any weights that you measured.
You mean the mass of the air?
The mass of the thing you're getting the balloon to carry.
So it was connected to a force meter, as we mentioned, and so the force meter was tied down, so there was minimal movement.
Could you explain as to why? What do you mean by minimal movement?
So we connected the muscle to a force meter, and since the force meter did not move, the muscle also did not. So the muscle was not able to drag the force meter around.
So you're saying the muscle did not move. The force meter didn't move because the
Yes.
muscle. Okay. Does the balloon size slightly change before you start adding air into it?
What do you mean by slightly?
So does the balloon size change? You use a constant starting balloon size in your experiment. For example, do you let it rest with no air inside before you start?
Yes.
Okay, time is up. 3 minutes to prepare. Component, please take control.
Hi, my name is Morgan, part of No Nighters, and I'm going to be opposing on number 2, air muscle. So first of all, the problem statement is to place a balloon inside a cylindrical net, as is sometimes used to wrap garlic and inflate it. The net will expand and shorten. Investigate the properties of such a muscle. So this is the ideal structure of investigation, which is a balloon enclosed by an elastic net and then attached to like a variable weight. So the weight would be the parameter and the balloon would be suspended in air. Then put the system, measure the values of how the pressure is affected, and then put the system in water to measure the volume, because water is a better way of determining the volume. So the opponent structure, what they did was they observed the behavior of the balloon in the net without any weight. And then they divided the phenomenon into 3 stages. So one, they did a linear growth. And then second, they measured like how it plateaus. And then third, they measured like the first stage. And then they also assumed that the net is a constant thing. So the modeling for the opponent is that they modeled the muscle as a spring. So they used a spring model to see like the movement of the balloon. And then they also calculate the rate of change of the volume using its geometry by splitting it into half cone and half sphere. And then they also predicted the height and the radius of the muscle over time. And they calculated the force exerted on this muscle. So how the muscle at different volume of air is pumped in, the force is effective. And then lastly, they compared. So they tested different parameters effects on the force, so the maximum force, and then the length of the net. Then they found like the critical point. So the pros and cons of the report. First of all, the pros is you have a clear diagram showing the qualitative observations of the graph, and your graph starts clear and laid out. And you have error bars to justify for like accounting for a range of values. But for the cons, your axis titles were small, so it wasn't really explained or visible. And you could control more variables in the experiment because you measured a lot of parameters and a lot of different variables that instead of keeping to a constant. And we also assumed that the net was a constant surface area, but this may change because that's not always like the net of one that is usually used to wrap garlic. So another con is you also didn't account for the temperature because as you put air in, the temperature of the system changes. And I would like to go on to the discussion summary.
You want to discuss?
Yes.
Yes. Before?
So first, can we talk about the experiment measurements and the variables you used to measure the experiment? So you said you used you measured like the linear part of the experiment?
We measured all 3 stages of the balloon as we showed. So each experiment was done until the balloon and the net first. Yeah, so yes.
So could you explain why you think this model is the best one for the experiment, because there's a lot of different factors that in your model is not accounted for.
For example, what parameters did you think that my model neglects?
Because the balloon doesn't exactly fill in all the area of the net, because as you can see from your photo, is a part on the side of the net that the balloon, because it's spherical and the surface of the balloon is more like a sphere, it cannot account for edges, just as the one shown from the net.
Yes, but I think that for example, the width of the entire muscle is kind of dictated by the balloon's width, as you can also see in the picture. Because the balloon is the main cause for the net stretching, and so the balloon is also the main reason why the net stretches, and so I think that it's the main factor that determines the width of the net, which we included in our theory.
So for your net, even as it expands, the elasticity of the net may vary, because the net can expand, and then the elasticity of the net, like as more balloons or like more trials are being used, this elasticity value changes because the net is constantly being pushed from its limit.
Yes, I agree. So we also observed that in our experiment that after the balloon reaches after we continue to inflate the balloon and the balloon's volume continues to increase, the net will start to break a bit, and before it actually bursts completely. So I think this is also why we observed this range where the force exerted by the muscle stops increasing.
So did you do anything to account for this burst of the net, or to prevent it, such as changing the net or anything you changed?
I think the bursting is inevitable, as no matter how strongly the net is, I think it would be possible to inflate the balloon until they burst. And even if the net was strong enough, perhaps the balloon would not be strong enough.
So even if the net was strong enough, the balloon won't be strong enough to burst the net? Is that what you're saying?
Kind of. So anyways, because we just continued our experiments until they burst, so I think we managed to account for all of the stages of growth in the balloon.
So you measured it until the balloon bursts. Then if the balloon bursts, the net then contracts back.
No, the net also breaks as well.
So you do account for the net breaking?
Yes.
So what did you do for the next steps if the net breaks? What did you do to the experiment did you use the same net or same type of net with the same thing for your next trial?
So as I mentioned before, all of our experiments were conducted until the net and the balloon broke. So each time we did the experiment, we completely replaced the balloon and the net to prevent any wear and tear of the balloon or the net.
Then if you replace the balloon and the net, doesn't that give you a new constant of the elasticity of the material and of the net and the balloon? Therefore, for your different trials and measurements, you would have different constant elasticity values.
So our balloons were both on the market and produced by the same manufacturer. And so the elasticity should be, and also the balloons were mass produced, so also the net as well. So the elasticity and some other parameters should be relatively constant. And also, to prevent any errors, as you mentioned, we also did multiple experiments for each parameter, hence the error bars.
Then could you go to page 6? Or
6?
You have a graph where it shows that one. Oh, can you go over a little? Next one. Next is a graph where you have because you said the pressure doesn't change, right? This one.
I think the change is quite small.
But couldn't the pressure change be the part where it keeps fluctuating on your graph?
Yes, but I think that this range is so as I mentioned, we did measure this pressure, but so we controlled how we inflated the balloon. So the pressure change is just the results we received from our experiment.
But as the pressure changes, wouldn't it also change the system and like the system of the balloon? So therefore, as before and after, like for your time before 20 and after the part where it starts plateauing again, that part, like even though the pressure is the same, the system inside has like experienced some sort of change. Did you account for that?
You mean in my model?
Yeah.
So our model mainly, as I mentioned, mainly focused on the volume. So the volume. So and anyways, since we did measure the pressure, it is very easy to just input the pressure values into the model.
So even though it's very easy to input the pressure values into a model, you didn't do so after you realized the pressure actually fluctuates?
Well, first of all, I think that the fluctuation in pressure is more of an experimental result than a factor we control. And yes, perhaps I will, and as for inputting the numbers to the model, perhaps I will try to quantitatively compare my other parameters like I mentioned in the future.
As you insert air into the balloon, for it to measure like how much the force how much it exerts on the force because as it expands, did you account for how the temperature inside the balloon also changes as more moles of gas are added?
Like I did not measure the temperature, but I think that the temperature change would not be significant.
Because I think it may have an effect because as the temperature changes, the volume does also change due to the temperature, which then would account for like a different value of what you measured for the volume and the pressure.
So first of all, for example, I did measure the pressure and the pressure for the entire duration, which it does affect, does account for that, and also I think that the temperature change is not significant.
So going back to our net elasticity, an offer of a better model would be to keep the net constant, because if you have a constant net, you measured the changes and the parameters based off of this constant net, which then you would have a normal, like a constant tolerance of the net.
Can I ask what you mean by keeping the net constant?
So keeping the same net for like many different trials that you have, then changing, what do you think is based off of that?
As I mentioned, the net breaks. So I did every experiment until the net break. But am I correct? So what you mean is that I should try to do experiments and measure or like consider how the net is being worn down but does not break. Is that what you mean?
Yeah. So as you use a constant net, even though it may like, as you said, being worn down, but it has the same tolerance for all the nets. So like, if you use one net, the tolerance is still the same.
I think that if I did not change the nets, the wear and tear on the nets would be quite significant, and so some parameters like the elasticity you mentioned would not be the same.
Okay. Lastly, could you please explain why you think your model for measuring the volume is the best? Like, is a more like one that accounts for all of that?
So as I mentioned, I fitted. So I compared. Yes, I compared my model with my experimental data and found it to fit quite well.
Okay. Thank
Okay,
you.
time is up. Opponent, summarize your discussion.
first of all, so we discussed going to the breaking point, which is like believing that the tolerance of the manufacturing isn't enough. So, for example, like some experiments didn't go until the breaking point, so therefore, with a net that doesn't like break as significantly. And next, like we suggest swapping to stronger net or changing the net because it allows for like multiple trials with constant like net and then the changing one. And then we also talked about the temperature because the temperature should be controlled due to the natural like gas law because it states that as like more moles is added into the system, the temperature will be affected due to the increase in moles. And then lastly, the volume measurement and how they measure their volume in the experiment.
Okay. Reviewer question.
So they only ask, do you think the force is related to shape of value?
The value of what?
The shape of value, the shape.
The shape of balloon?
Yeah.
You mean the volume or the shape?
Yes.
I think it's both, but I think it mainly depends on the width of the balloon.
So you don't have. The force is related to the shape of the balloon.
Yes.
Yes.
Is it, wait, could you ask?
The force is related to the shape of the balloon. Yes or no?
Yes, because force is pressure over area.
So do you think it is reasonable to assume the muscle into a spring?
I included some terms, as I mentioned, into the efficient K. So K also accounts for some changes in pressure and length, and also it is actually supported by a lot of relevant literature.
So you think it is can be used the foot law to describe the M muscle, right?
Can you
do you think it is reasonable to use Foot's law to describe the spring?
Yes.
What do you think?
I don't think so because using a spring model would then say, because if you use a Hooke's law, K is a spring constant, which you cannot measure using a balloon.
I want to ask, you mentioned you separate force into three states, right?
Yes.
Yes. So which state do you think it is most likely to have muscles phenomena?
I think if you're talking about the muscle, perhaps the first stage would be more applicable for example, a muscle if you were to apply it for more regularized conditions.
Could you ask the question?
But which state do you think it is like a muscle phenomenon?
I think the non-linear stage, the plateau part.
Okay, so you think it's linear or non-linear?
I think that the linear stage, in the linear stage, the muscle does not break.
So linear stage, okay. And I want to ask you, do you think the body will add the shape of the neck band and the body will eventually become a steady state, which is not the shape of the body and the neck band will not change anymore.
I can say that again.
Do you think the body and neck band will eventually don't change anymore?
They break eventually.
Yes. Do you think this is or not?
Yeah, it will change. It will break eventually.
Yes. What do you think?
No, I don't think so because as pressure keeps on increasing, the volume reaches a constant, but the volume keeps increases even as the pressure comes on.
That's it. Thank you.
Okay. Prepare of the reviewer 2 minutes.
Continue from the 17th and 11th, go to number 3, product and muscle. So I'm first going to review the report. Report in observation, they found that the pressure is constant and they found a lot of relation between the parameters. But they didn't provide constant boundary condition precisely. And in theory, they use a theory for radius and length. And they have a straightforward theory and it can be easy to understand into the Hooke's law. But they didn't have a quantified explanation of force, especially in three states of force. They didn't have a pretty well theory to fit this. And for the experiment, they find a lot of relation between force and parameters. And I think the setup, like the pressure, like the force measurement, is pretty precise. But I think there are two last data point and parameter to show the trends and some quantified relation between parameters. And they didn't connect the experiment data to a theory. And for analysis, we think they use a lot of geometric explanation to explain the data on method. And I think first they explained the unfettered data well, but they didn't have the physical meaning to explain the unfettered data in the geometry relation, and they didn't quantify the explanation. For the position, we think in the presentation, they suggest a better pattern to some measurement, and they conclude the report as well. So, without short question, they ask about the force attached, whether a force attached on net length and the initial volume size. And we think the question is pretty short and clear, but I think they misunderstood the presentation from the report alone. For the discussion, they think the break stage should be considered, and temperature should be considered, and pressure change should be considered. And I think they did agree well on a lot of discussion about the experiment, but they didn't quantify the theory a lot. So for the key question, in theory, the important thing, the models might be the best one, and shape of value and force. But reporting is the shape is similar, so it's not need to consider around shape. So I agree. Well, I agree for the opponent. And the experiment, the important thing, the pressure will change in the pressures relation, and the reporting pressure is quite small and did not need to consider. But I think the reporter should quantify the change of the pressure, and I think this is really important because the pressure might affect the pure from force is time domain. And for the experiment, furthermore, the important thing you need to consider temperature, but reporting it's not pretty important, and for the change of temperature is pretty small. But in my opinion, I think opponent idea is pretty great, and I think temperature is pretty important for the values. Okay, and that's the opponent thinks the break stage should be considered, and the reporter said they separate the state into three parts, which is the linear and nonlinear and the collapse. And I think the break state has no physical meaning, so I think we should only consider about two states. And I think temperatures need to be considered. So our question is, we ask about the shape and volume of the volume is related to the force, and Hooke's law is reasonable. And the opponent thinks that yes, the force is related to shape and volume, and the reporter thinks yes, the force is related to shape and volume too. But Hooke's law is not applied for, and yes, it cannot be used. And I asked which state is the most like the phenomenon. The opponent said the linear state, the reporter said non-linear state. And I think, in my opinion, I think it's linear state. And last I asked, volume will eventually be constant, and the opponent replied yes, and the reporter replied no. I think yes, because I think the volume will eventually be constant. That's it.
Okay, so for my concluding remark, first I varied some parameters, including the length of the net, and I also compared nets with different mesh sizes, and also compared different sizes of balloons. And so for my experimental setup, I had a rather controlled experimental setup. So I had a force sensor that was tied to a hook on the ground so that it does not move. And I was able to accurately measure the pressure and the force exerted by the muscle and inside of the balloon. So for my quantitative theory, I successfully used my geometric approximation while keeping the model simple. It was able to apply to my experimental data with some constant I derived experimentally in other experiments I also mentioned. And so for my about the discussion with the opponent. So first of all, I think that the wear and tear will be significant on the nest. So I changed the nest each time, and also I did multiple experiments for each parameter. So I was able to account for some small deviations in the nest. And also I also did account for the pressure changes by measuring how the pressure changes inside of the balloon, as I mentioned with the gas pressure sensor. And also, while the I think the Hooke's law is actually applicable quite well, at least to the linear stage. And also, I think that the balloon bursting is it will happen no matter what it's quite inevitable. So I also did account for the bursting of the balloon, and also I burst the balloon each time. And also, I think that the expansion will have little effect on the temperature. Thank you.
Okay. Question of June. June, any question?
So I ask a question for all of you. Do you believe the temperature is an important parameter for this experiment? If you believe temperature is a quite important parameter, how to modify the model including the temperature parameter inside? If not, tell me the reason why temperature is not so important. So who will answer?
Okay, I'll go first. So my interpretation of the opposition's question was that the temperature inside of the balloon would change due to the changing volume. And I think that the temperature the changing volume, well, it might change the temperature, the effect will not be significant. And if the opposition meant the room temperature, I did the experimenting, it was under room temperature, and so the fluctuation will be very small.
I think the temperature should be accounted for to some extent, but you should mention how the temperature is affected, but it's negligible because it only affects due to the amount of moles you add in. So because you have more moles and more pressure, the temperature changes by a slight amount, but it's not like as significant for you to measure as like a whole new factor.
I think the force is mainly related to the values of the volume. So I think the temperature can change the relation between the pressure and the volume. So it is important to know to check whether the temperatures has a different or not.
Any question? So I have one question for everyone. In the problem, do you think about pressure, force, volume of air? What is important?
Do you think the most important parameters affect the
Air pressure or volume or temperature?
I think it's the value, which is the shape of the value.
I also believe it's the volume.
I think it's also the volume because the pressure reaches a constant, but the volume continues to change.
Thank you. Maybe small time. Okay, please. Okay, everyone, let's go. Please, for the reporter. Let me. 5, 5, 5, 6, 7. For the opponent. 6, 5, 6, 5, 7. For the reviewer, 7, 7, 7, 6, 7. Okay. Out. Break this time. Okay. 休息10分钟哦。